Thank you for this kind introduction. It's a real pleasure to have the opportunity to present our work today. I would like first to acknowledge my co-authors, Laurent Michel, Associate Professor in Lyon, in my lab, and Andrea Armonico, the students who mainly done the works during his PhD. So we are going to deal with monitoring of reinforced concrete structures using quite a smart FRP that allows to identify the damage process that we may have during the bonding process. So maybe to start, I would like just to outline some results coming from my PhD. It's a bit far ago, but at that time I worked on double lab shear test using external bonding FRP, work on fatigue, creep, aging process at that time. And at the end, I came with some basic modeling and relation, allowing to fix the limits that should be allowed for the internal shear stress developing between the concrete and the FRP, depending on the lifespan duration you should have and temperature. So it was a very useful model. And as some prospects at the time, at the end, I conclude that I would like wants to be able to test this modeling I've done 25 years ago on real case study bridges, and for that there is a need to develop some monitoring process to be more comfortable from what we get from the field. So it's my pleasure to try to show you some outline and some new results 25 years later on this topic. So the presentation will basically start with the introduction, laboratory study, validation we have been able already to do, and conclusions. So, as in North America, French situation is not very good for bridges. Recently, several of them collapsed, and so the government asks and requests some survey to try to identify the weakness of these bridges. And our bridges are made about 30% of them of reinforced concrete structures, and basically almost 10% of these bridges need very urgent reparation, strengthening. It means about 20,000 bridges need repair. In the past 3 years, government put millions of euros on this, and they have been able to strengthen only 100 of them. So it will took us maybe 200 years to retrofit all of the bridges. Main techniques used is quite common, nothing new about this, since this technique is well known since maybe 20, 30 years. It's external strengthening of bridges for flexural and for shear. And the main thing is, which is new is that owners want now to know when their bridge is strengthened, for how long they can continue to use it, because you cannot easily tell them that it will be okay for the next 100 years or 50 years, or maybe it's only for 10 years. So the idea is to try to identify the risk of failure of these strengthening structures. Basically, we all know that there is intermediate shear crack that could cause the debonding on the FRP, or we could have collapse at the end due to pitting. All this is perfectly identified. There is several equations in literature and design code allowing to reduce this risk and to be able to correctly design these beams. But actually, due to fatigue, aging, creep, the idea is to try to be able to monitor this during time. So, to do that, basic tools that could be used is fiber optic sensors. It's well known, well used in Canada since a while, and in other countries, already used in reinforced concrete structures to monitor mainly the strain along the length where it is placed. So with that, you have a strain profile that could be interesting for us. More recently, due to image development and computer basically going more and more strong and fast in calculation, they have been able to develop structure by motion with these clouds of points on a structure, you are able to build a model. This model gives you a numerical point of view of your structure with a quite high resolutions. It's quite very interesting to see what can be done with software now. And with that, we expect to be able to monitor the structure. For this, to go quite quickly, we developed first a laboratory testing with 14 samples. The idea is to combine different way of get information about the structures and to see what we can do with them. So laboratory studies start with some objective. Objective is to better understand how the debonding occurs and to see how can we anticipate it and monitor it. Basically, there is a lot of theoretical model existing in the field since maybe 20 years, and basically we see some model that's appearing in literature showing this high stress appearing in the interface localized around the crack. That's the idea, is to monitor that and to provide a methodology for measuring damage and crack processing in reinforcement with structures. For this, first, we are going to use internal fiber optic sensors along the FRP. This will allow us to get some strain profile. Then we'll combine this with digital image correlation, well known today in our labs. This allows you on the lateral surface to get a grayscale image. By comparing the two images between two level of loads, you are able to get a strain or displacement field, allowing to build the crack monitoring of your structure. So for this, the 14 beams have been prepared, test and a 4-point ball bending test with 3 steel ratio to have very low and very efficient strengthening of FRP, and so quite normal strengthening one. We use only 1 ratio of FRP system. The system used was external bonding FRP. Some results, because we don't have a lot of time to develop all the PhD that have been done, but just to show you, these informations come from the two, this is from fiber optic sensors in the FRP, this is from digital image correlation. What's quite interesting to see is, depending on the level of loads, you have some peak stress on the FRP just corresponding to the level of cracks you have. It's quite normal and logical, but what is very interesting is that if we integrate this strain profile, you are able to get a crack opening thanks to the optical sensors, but also for digital image correlation. And we can see that in function of loads, we are able to monitor the crack, and so we thought that if we monitor the crack, we should be able to know how behave the FRP by an inverse method. Another interesting result is that if you are able to get the strain profile, you are able to get the stress in the interface by simply differentiate the two different strain you have in FRP in function of the length of immersement. Based on this and on the mechanical properties knowing of your FRP, you are able to get the stress in the FRP. That's the model developed already in 2000, and we try to get the results coming from the literature basically with our experiments. You have here the strain profile, the integration of the strain profile, and you can see the shear stress distribution. When the load is very low, the stress is very low. But what was very interesting in the development of all those tests is this example of results we get. You clearly observe here that when the crack propagation continue to develop during the loading increasing, the stress locally gets quite very high and the debonding locally appear. It means that these techniques should be able to detect the local debonding of FRP and to anticipate maybe the failure. So basically, thanks to this first study, we get to a small-scale, full-field validations. So we develop large-scale beam, 5 meters length, do done some static tests to check if everything was correct, and do some fatigue loading. I don't go too much into detail because we don't have the time, but for the fatigue loading, we done outside our lab. We developed some specific tools in order to apply a fatigue loading thanks to dead load applied here and a pneumatic jack allowing to push and to apply the fatigue loading. We monitor that with 3 tools, fiber optic sensors, digital image correlation combined with structure by motion. For structure by motion, since it's quite a new equipment we have, we wanted to control what we get from these new tools of scan of structures. We use a ground control point to have a GPS control point and a quality control point that is checked on the structure by an external tools, which is quite not so difficult to have. Some results. You have here the normal beam without any strengthening. You can see some very big stress all around the structure. We monitor the fatigue loading on a quite high level, 0.8 of yielding stress in steel. And you have here the blue one is the one with the strengthening FRP. What is very interesting is we combine this monitoring with digital image correlation, and again we confirm that we can combine the 2 tools to correctly monitor what happens on the structure. With structure by motion, this is some kind of cloud of points you get from the scan. This can be cleared, cleaned, so that you are able to get the numerical version of your structure. 5 meters span, and we get the resolution of 0.02 millimeter, so that's a very good accuracy. Some results very rapidly. We get some interesting things by the curvature measurement, vertical load measurement, but also the crack opening thanks to this tool. So we could thought that basically by scanning the structure, we would be able to get to the crack, and if we get to the crack, get again to the internal stress without using maybe fiber optic sensors or combine the 2 if we need. That is what we have done, and you have some strain profile identified here, and their evolution during the time we get during the PhD, 6 months duration, to monitor how the stress evolved in the FRP during the fatigue of these beams. So I don't have enough time to go in all the details of the work done by Andrea, but mainly we have seen that passive monitoring is possible for such kind of structure that could be anticipate maybe the failure in future or monitor and to secure the owners. We can combine the tools, FRP measurement by fiber optic sensors or by scanning the structure at time to time. The problem is that you collect a lot of data when you do monitoring, so I think the next step is to do some active monitoring, maybe thanks to II or to do some live monitoring to avoid engineer to go to the field, get some measurements and get informations. Because depending on the time you are going to do that, you maybe lost the damage of the structure. So there is a lot of work to continue to work on. And I would quite agree with you that we have a lot of work to do for several years, I think. Maybe not 25 years again, but for several years. Thank you for listening.